Now it's the turn of one-sided limits. So far we've discussed limits that are two-sided in nature. So to check that the limit of f of x as x approaches c is a number L, it was necessary to check that f would approach L as x approached c from either side of c, meaning for values of c slightly greater than or values slightly smaller than c itself. But it happens that in some instances that f of x may approach a number L on one side, uh, but not on the other side. It may approach a different number on the other side, or may not approach anything at all. Or even worse, f may not be defined for values on one side of the point C. So in that case, it's useful to introduce a notion of a one-sided limit. And there are two one-sided limits, one corresponding to the left and one corresponding to the right. The notation is like this: lim of f of x as x approaches c minus denotes the left hand limit, and the lim of f of x c plus denotes the right hand limit. So in the graph, if this is c, if we're approaching x from the left, it means that we're approaching c in this direction. So we're letting the values of x get closer and closer to c from the left. And in that case, for instance, this number here, L, would be the left-hand limit of f. So the same holds for the other side. So if you have the right-hand limit, if you consider the right-hand limit, you will just look at what happens on the right side of c and see whether f of x is approaching something or not. And then you will call that your right-hand limit. A very important observation is that the limit, as we defined it in the previous video, the limit period, it just limit itself, exists if and only if both one-sided limits exist and are equal. Okay, so in this graph, for instance, here you see that f of x, this graph, you see that x is approaching, f of x is approaching L as x approaches c from the left, and also f of x seems to be approaching a different number over here, up here, as x approaches c from the right. But these two numbers, this mystery number here and L, are not the same. But if these two numbers happen to be the same, then it would look something like this. This is c, and we have a function. This one may not be defined at the point C. Remember, this is not important. If you forget about the left-hand side for a minute, you see that as x approaches c, the values of f, so this height here, are approaching L. And the same happens when you approach x from the left. So in this case, the left-hand limit of f of x is L, which happens to be the same limit as x approaches c from the right, and then they're both equal to then the limit, the actual limit of f of x, as x approaches c. So there's no need to talk about right or left hand limits anymore, because they're both these two left and right hand limits approach a certain number, and they're the same number, and so the whole limit exists. An example of a function that has a left and right and limits that are not equal is the function. I mean, this is completely equivalent to the example given in the book involving the absolute value function, but this way of presenting this function will play a role in subsequent sections. So I'm just going to say this is a function that takes in the value -1 when x is less than 0 and is 1 when x is greater than 0. So what does the function look like? So for values less than 0, so this is suppose this is -1, the function takes on the value 1, and then for values larger than 0, then it takes on the value 1. So this is f of x. And so as we approach 0 from the right, we see that the limit from the right is 1, while the limit of f of x as x approaches 0 from the left, so if we approach from this side, then f of x is actually equal to -1 all the way, so it's certainly approaching -1. Notice here that this graph has a hole when x is equal to 0, so f of x is not defined. It's not defined at x equals 0. But that's not important. However, it still has a one-sided limit. Okay, so the reasons why a function may fail to have a limit are different, and they may also imply the non-existence of one-sided limits, at least for one of the sides. And so some a function f may fail to have a limit or even a one-sided limit at x equals z. So let me rephrase that. So, or the function may fail to have a limit, or say a right or left and limit at x equals c. If the function becomes unbounded. Near the point. However, this is not the only thing that could go wrong. Take, for example, the function sine of 1 over x. So if we look at the function f of x equals sine of 1 over x for x greater than 0, then what happens if we try to compute the limit of it as x approaches 0, but from the right? Remember that we're just focusing on the function when we look at positive values of x. This function, well, sine is always, notice that sine of anything is always bounded, so sine of any number is always bounded between 1 and minus 1. So the function cannot be exploding when you get closer and closer to 0, because the function is bounded. However, if you look at the graph of the function, sine is a function that oscillates, so this is 1, say, and this is minus 1. So what happens is after you get closer and closer to the origin, the function sine of 1 over x starts oscillating more and more, and oscillating between minus 1 and 1. So that means sine of x is not approaching anything. So as x gets closer and closer to 0, sine of 1 over x takes all the numbers, takes on all the values between minus 1 and 1, including those two values, infinitely many times. So this oscillating behavior tells us that it cannot be approaching anything, because it's not getting closer to any number in between minus 1 and 1, because it's actually going from minus 1 to 1 infinitely many times. So if it were getting closer to a number, say 1/2, then you start to see a trend where it doesn't move too far from 1/2 as you get closer to 0. But this is not the case. So you cannot have a limit. And you cannot have a one-sided limit in this case. So the one-sided limit, so the conclusion, because of its oscillating behavior, this does not have a one, or here we were just considering the right hand limit. At x equals 0. Okay, so there are many ways in which the function may fail to have a one-sided limit or a limit in general. Not only the function becomes unbounded nearby, but also when it oscillates. Man, this is the takeaway of this discussion. Now, what about analyzing graphs, for instance? This is something that you may be asked from time to time. This is a kind of graph questions. So I'm drawing some information from the graph regarding the left and right hand limits of a function. Then you can see suppose this is the function f. Then as we approach the value 1, we can see that f is approaching either 2 or 1, depending on whether you're on the left or right hand side of the graph of 1. So what does this graph tell us? That the limit of f of x as you approach, say, 1 from the right is, so if we move in this direction, then we're getting closer to this value here. And that is 2. Sorry for my poor drawing skills. Instead, if we approach 1 from the left, we see that we are approaching 1. I mean, at least that's why I intended meaning this graph. So if we approach 1 from the left, we'll see that we're approaching 1. So there are 2 left hand limits. And if we look at what happens at 2, in the same way we would conclude that the right hand limit as we approach 2 is equal to, so remember we're approaching from the right, so from here that will be equal to 2, while the left hand limit of f as we approach 2 would be equal to just, would be equal to 3. this case. Would correspond to this number. So if we move in this direction, then we will be approaching 3. Okay, so that's what we can say about one-sided limits. We'll continue next with infinite limits, and then we'll just cover a couple of examples and finally move on to the important, very important limit laws.